At Moffett Field, south of San Francisco, scientists have been researching into the details of crater formation by firing projectiles at high velocity down a barrel into a bucket of sand set on the floor of an evacuated chamber.
We can produce a hole in the ground. We can produce it with a very small object. A quarter-inch ball might produce a 20-inch diameter crater. It'll look conical in shape, but that won't be necessarily what a lunar impact crater will look like. Here's an example of a lunar crater, and to give you an idea of scale, the meteor crater, the Barringer crater in Arizona, would probably be about the size of this crater right here. This gives you an idea of the amount of energy that's involved when one of these events actually happens. It's a catastrophic process that is very difficult to imagine, and these experiments provide us only sort of a small glimpse of really what's going on.
In this shot, a thin layer of red tempera has been spread over the surface of the target so that the trajectories of particles in the surface layer can be followed in detail. The chamber must then be evacuated slowly. An electronic control system will fire the gun, having first switched on 3 high-speed cameras and their lights to record the impact in slow motion.
Well, I hope it works.
I hope so.
Any bets?
No.
If it works, I'll get you a donut.
Oh, if it doesn't, I gotta give you one.
That's right.
I'll get you one with the hole.
Every time you do one of these things, it's a little bit different. I don't know, it's sort of like opening a present. You never know what exactly is going to happen, especially when you take perhaps a day preparing a target, and then suddenly to have it work. I feel like I... And I'm constantly surprised. This is what's the beauty of doing experiments. You never know what's going to happen next.
Heavy.
Ah, great. That's great. Okay, that did just what we expected. Here we can see where the red tempera that we had on the surface of the target has been covered by the lighter material that was below it. And you can see the decay, and eventually that of the thickness of that ejecta, and eventually it gives out about here, where it predominantly becomes red. And as you go farther out, you can see just primarily red clumps that have impacted. And these would have produced secondary craters had they been formed on the moon at a much larger scale.
And this is what the cameras recorded. An impact slowed down to 1/16 its normal speed. What do such pictures tell us?
One of the things that we can tell out of these experiments is that the process of cratering is a very orderly process. It's not this chaotic jumble that you might envision by looking at an old war movie or looking at the nuclear explosion. It looks very like a chaotic jumble, a cloud. Instead, in a vacuum condition, which we have for the moon, it forms a nice series of conical shape, inverted cones that marches outward. And as it marches outward, it doesn't change its form very much. And this marching outward is a result of the locus of ejecta material coming from the inside first and at the highest velocities and contributing to the top of the ejecta plume. The material that is down at the bottom of the plume is coming from deeper in the crater. And even after the crater is formed, this ejecta curtain simply keeps on marching outward in a beautiful, regimented way. And that's in contrast to what happens if we introduce the effect of an atmosphere. And here we find that the beautiful, symmetrical, even transparent ejecta curtain that marches outward is replaced by a much more complex curtain. We find that the material seems to be drawn in at the top and bulges out at the base. It's a very fundamental difference between impact in a vacuum and impact in an atmospheric environment. The net effect is that we can produce very strange-looking craters. They're strange in comparison to the moon, but they're dead ringers for many of the craters on Mars. And by varying the atmospheric pressure, increasing it, decreasing it, we can go through and look at almost all the various morphologies that we see. Now, here we've taken two photographs, cut them in two, and then pieced them together. The right photograph is of Mars. The left photograph is of a crater that we produced in the laboratory. And we see that they're very similar. This is in a completely anhydrous environment without water. And we find that we form this ridge. And this ridge continues around and at about the same distance that we find for the Martian craters. We believe this ridge is produced by the dynamic motion of the atmosphere in response to the cratering event. It's that curled and that bowed ejecta curtain that we see. And behind that ejecta curtain, this is sweeping up material and then depositing it in a ridge. Now, that's just the atmospheric effect. Now, if we add water, then we add something else again. We add a lubricant. We add the possibility that once that material hits the ground, it'll flow. We add the possibility that the sizes of the ejecta may be decreased even more. So the laboratory gives us a feel of what may have happened for Mars.
At first sight, the atmosphere of the Earth looks complicated, but patterns of atmospheric motion can be identified. Some of the patterns are predictable, and some are not. A band of cloud within the tropics is evidence of Hadley cells. At higher latitudes, cyclonic features can be identified. Hadley cells are caused by hot air rising at the equator, migrating polewards, and descending at higher latitudes to return at low altitude. They are more pronounced over the land, which is hotter. The west-east rotation of the Earth results in a Coriolis effect, which is manifest as a spiral motion. Friction drags this spiral open. This pattern is predictable. The Hadley cell motion extends over large distances, but at temperate latitudes is quickly dominated by turbulence. Eddies from the Hadley cell form the cyclonic features which dominate British weather. Unfortunately, cyclonic features are quite unpredictable. An extreme example of a cyclonic feature is a hurricane, which can involve the complete breakup of a Hadley cell. Hadley cells and cyclones can also be identified in the other planets of the solar system. The dominant pattern of atmospheric motion on Venus seems to be a single Hadley cell, extending from equator to pole with wind speeds greater than 200 miles per hour. Solar radiation does not readily penetrate the cloud layers, so this motion is not driven by the surface of the planet, but by temperature gradients at altitude. The Hadley cells themselves drive circulation at even higher altitude by friction. This is the movement we see in the upper atmosphere. Under high-speed east-west cloud movement, the rotation of Venus is slow. Why the wind speed is so high and in the opposite direction to the slow rotation of the planet is not known. But a contributing factor is a heating of the day side, which sets up pressure differences in the atmosphere, resulting in an east-west thermal tide. Moving out to Jupiter, atmospheric circulation can be seen in bands of cloud moving east-west around the planet. Different bands move at different speeds. An exercise is about to follow involving these cloud movements. Your video notes explain what to do. If you have not already read these, you should stop the tape and do so now. Mark the position of the ringed spot, and also mark the width of Jupiter at the same latitude. Now mark the width of Jupiter at the equator. Also note the time on the clock at the top of the screen. I'll run the sequence in a few seconds. Mark the furthest point of the dark spot and the corresponding time. Don't worry if you don't get everything at once. I'll run the sequence several times. You might like to play this sequence more than once. Now you should calculate this wind speed on Jupiter. Jupiter's atmosphere is rotating much more rapidly than that of the Earth. With this faster rotation speed, a model based on Hadley cells and an atmosphere less than 100 kilometers thick produces a banded structure. Here you can see closed rings which represent eddies produced at the boundaries of well-defined bands. Cyclonic and anticyclonic features are also present. The most famous of these is the Great Red Spot, which is anticyclonic. This is a giant whirlwind surrounded by eddies. It might have persisted for centuries. Saturn has a much fainter banded structure than Jupiter. We can only see it here because the image has been enhanced. Saturn also has storms. These images show the Great White Spot, which developed over a few months and eventually encircled the planet. The white spot is cyclonic, but is not persistent like Jupiter's Great Red Spot. When Voyager flew past, there were no large-scale features on the planet. The spin axis of Uranus is heavily inclined, so although its weak banded structure appears concentric, it does follow the spin of the planet, and is similar to that of Saturn and Jupiter. These bands are clearer on this enhanced still of the planet. Take the enhancement away, and Uranus appears almost featureless. By contrast with Uranus, Neptune does have some clearly visible cloud movements. Here are two features seen from above the South Pole. The most notable feature is Neptune's Great Dark Spot. There is also a feature called the Scooter. Like Jupiter, these features reflect the differential motion of the bands of Neptune's atmosphere at different latitudes. But studies of Neptune have shown that the speed of the fast-moving Scooter is also different to other features at the same latitude. Why might this be? Are latitude and longitude the only variable positions for an atmosphere? From Neptune right back to Venus, similar types of atmospheric circulation can be seen. Now this is most surprising. Think of the differences in sunlight that the planets experience. At the extremes, the energy flux on Neptune is only 1,000th of that on Venus.
In Chapter 8 of Block 2, you will have encountered mass spectrometry. All astronomers are aware of the electromagnetic spectrum, but in planetary sciences, the mass spectrum of the elements is something which provides important information about solid materials. Mass spectrometers can be enormous, occupying a whole room, or they can be small, like this gas source machine. The feature they all have in common is the ability to separate mass by passage through a magnetic field. A mass spectrometer is made up of a number of components. There's a means of producing ions, and these ions can then become accelerated, where they leave the source via a slit, and then they pass through a magnetic field produced by this magnet, and they travel in a curved trajectory before coming to a detector or collection system which provides amplification. If the ions enter a region of constant magnetic field, they have the property of moving in a curve. Ions with less mass are bent more than those with more mass. By separating ions of different mass, we can learn what elements are in a particular sample. But perhaps the most important property of mass spectrometers is their ability to separate isotopes. In Chapter 8 of Block 2, we saw how oxygen isotopes can be used to detect heterogeneity in the solar system. Isotopes are forms of an element which have different mass because of differences in the abundance of neutrons in their nucleus. Oxygen has 8 protons with positive charge. These are balanced by 8 tiny negative electrons, which can be considered for our purposes to have no mass. The balance of the mass of oxygen is made up of 8 uncharged neutrons, so that in total the common isotope of oxygen is 16 mass units. About 2 out of 1,000 oxygen atoms are not like this. They have 2 extra neutrons to give 18 units of mass. And less frequently, about 1 in 2,500, there is only 1 additional neutron, so that there is a small fraction called oxygen 17. Before going on, use the table in your notes to work out all possible masses of molecular oxygen that can result from combinations of isotopes of oxygen 16, 17 and 18. What are their relative abundances? If oxygen gas is put into the mass spectrometer, it produces ions with masses of 32, 33 and 34, because 2 16s will combine together to give a molecule of 32, a 16 and a 17 to give a 33, and a 16 and an 18 to give 34. There are other combinations, but they're a very low abundance. Those ions, focused through the mass spectrometer, arrive at the collectors, and if you put 3 collectors, then it's possible to simultaneously collect all the ions of interest. To provide information about the isotopic composition of any sample, such as a mineral, a silicate, or an oxide, we have to ensure that the oxygen is transferred to the gas phase. Sample preparation is of paramount importance because we have to make sure that all the oxygen is obtained and that no fractionation, that's artificially changing the isotopic composition, is introduced during the experiment. The technique is to displace oxygen from the minerals using very reactive fluorine gas at high temperatures. The procedure is to load small amounts, about 1 milligram or less, of selected materials into a carousel for investigation. The carousel is inserted into a vacuum chamber, and the samples can be selected by viewing with a video camera. The compound containing fluorine is introduced from a liquid nitrogen trap, and the meteorite for which data is required is heated by selectively focusing a laser through the optics of a microscope and scanning the beam backwards and forwards across the sample so that the reaction proceeds. The liberated oxygen gas is collected and taken into the mass spectrometer for measurement. When plotted on a graph of 17 oxygen, 16 oxygen against 18 oxygen, 16 oxygen, meteorite samples fall in various defined regions, quite different from Earth's rocks, which all fall on a trend called the terrestrial fractionation line. The reasons for such differences are discussed in Chapter 8. As I have already indicated, the minor isotopes of an element make up only a very small proportion. We have to be able to measure this abundance relative to the main isotope very precisely. The problem is that mass spectrometers are very different the world over. This mass spectrometer here is quite different from that one on the opposite side of the room. To overcome this difficulty, all the vacuum pipework you see here is to enable us to swap backwards and forwards between our sample and an internationally agreed reference material, so that the small differences can be measured and allow us to compare with results obtained elsewhere in the world and even in our own laboratories. The instrument swaps between the sample and the standard on quite a short time scale to obtain what is known as the delta or differential isotopic composition. We need to know this to fractions of a part per thousand. As I have already said, the approximate isotopic composition of oxygen 16 to 18 is about 500 to 1. To understand planetary processes, we really need to know whether this is 499.95 or 500.01 to 1.